this M2.1 analysis of fabric performance. So it's basically trying to reduce the heating demand and cooling demand over the year. And the things that we want to vary are the insulation, the thermal mass, air permeability, and the solar gain. So yeah, so in this standard, it says that your model, you should benchmark that. So one of the options to benchmark it is if I use the constructions for the baseline building, ASHRAE baseline building, 2016, and then I've chosen climate zone 5 because my weather file's in Nottingham. So when I run that simulation and I get the heating and cooling demand over the year, that's the benchmark that I'm comparing against. So I'm trying to improve on that benchmark. Yeah, so trying to improve on that benchmark. Yeah, it's just saying here that using search function reduces the number of simulations required versus the parametric study. Click next here. So these are basically the results that it gives. Maybe I'll probably show that and come back to
it. So, sorry, Duncan, how many variables was that varying?
There's 4. So it's this example here. So set the current project directory. So I just show the building quickly. You can see I've got one that M2 example benchmark. So that's the one with the ASHRAE baseline constructions. And this one is the one I'm going to vary. So one of the, if I look at my external wall, so I'm using this construction for my external wall. And to make it a bit simpler for me, I've just named this material insulation. So that's the layer of insulation. And I'm going to vary the thickness of that insulation. And then I've just called this one mass, and it's basically a concrete, and I'm just going to vary the thickness of that concrete. So that's the thermal mass that I'm altering there. To change the G value, what I'm doing is I'm getting this material layer here, and then I'm adjusting the solar transmittance value. So then that affects the whole construction. So, and for the air permeability, basically using that figure to work out, to estimate an air changes per hour figure. So if I go into here, and I currently have 0.15 air changes per hour. So that's the value I'm going to be editing as well. So I've simulated that with the benchmark, and I've got the results out. And then I've just hard coded those into this script for simplicity. So the benchmark is this figure here. So I've added these 4 variables. So insulation thickness, the thermal mass thickness, my air permeability figure, and solar transmittance. So that's just solar transmittance for that one layer of glazing. And then I've set the minimum and maximum values and step sizes and an initial value. So, and this is just very similar to the previous script in that I make copies of the files and put them in the current directory. I create this document object, so I new this document object, and then I make these variables to receive the variables from here. And then I just go and set them. So I'm looping through the constructions in the building, and I'm looking for a material called insulation, and then I set that based on the insulation thickness. Yeah. And I do the same for the mass. The internal conditions, I just run through each of them, and based on the air permeability, I'm just dividing by 20 to estimate the air changes per hour. If it's this is from SIBSI Guide A, so if it's in a high wind area exposed, suggesting divide by 10. If it's sheltered, divide by 30. The other thing is, based on your air conditioning system, you might expect when that's on that the infiltration drops, and so there's lots of different options there for how you want to model the infiltration. But I've just set an air change rate, and that will be all the time for the zone. It'll just be constant. And then this final bit here is I get my call construction, and then I find the third layer, which is the one I want to edit, and I set the solar transmittance there. And then I just have to make sure that I don't exceed the reflectance plus the absorbance plus the transmittance doesn't exceed 1. So this is kind of what this is doing here. So it's making sure the reflectance and the absorbance will sum to 1. And this bit's just retrieving the G value, so I'm not sure what G value that will give me. So I retrieve it here, and I put that as output. I then save my TBD file and simulate it, so from day 1 to 365, and create a TSD file. And here I make the TSD document, open it, and basically retrieve the results. So this is there's a function to get annual result, but it's quicker to actually go through the days and then the hours in each day, just because of the way the data is. So this is all this is doing, and I'm basically retrieving the cooling load and the heating load, and then I sum those in some CL for cooling load, some HL for heating load, and some result here. So that's the sum of the heating and cooling load for all the zones. I calculate this improvement based on the benchmark, so it just gives a percentage improvement. And then some result, I've set that here. So this is the thing that's being minimized.
That's your cost function, basically.
Yeah, that's the cost function. Yeah. And then because this is multiple variables, we need to use a different algorithm. So I'm using this Hooks-Jeeves algorithm. I mean, I can run it here, but it won't finish in time because it takes roughly 177 simulations because it's got all the various variables. So when I do run it, I get something that looks a bit like this when it's finished. So it's basically giving me these results here. So it's the thickest insulation I'd allow, and thermal mass thickness, and then air permeability value of 3, which is the minimum I stated, and then a G value of 0.4. And I achieved 23%, 24% reduction in the demand compared to the benchmark.
Yeah, so there's the graph at the top, Duncan. That's the sort of convergence process where it's sort of going through each of the various options, changing stuff.
Yeah, so I wonder if I can, if I run it, it'll start filling it in. So it'll be a bit easier to see if there's only a few on there. But as I say, this might take a while. So yeah, it's basically, if I look here at the mass, it's trying a mass figure of 150 mil, and then at this point it says, well, maybe I'll try a different mass figure. So it reduces it by 0.5 mil, and then that result isn't a minimum, or the gradient's in the wrong direction, so it goes back, and then it tries again. You can kind of see that here with the insulation thickness as well. So it's stepping up. It's running the other it's keeping these the same and running the other combinations, and then it steps up again. And then
where's the cost function? Sorry, Duncan.
Yeah, so it's here, this result, and it's just coming along the bottom here to this green cross.
Oh, okay, so that's the one that's going down. Yeah, okay,
yeah,
which is good.
Green cross. Yeah. So it's basically taking in turns to change a variable and then seeing what happens to that result, and then it tries to change the next variable. Yeah, so these examples will be available for download in the link in the email that we send out. So yeah, I guess the other is it's starting to plot sequence. Yeah, so this is that BREEAM document section here. If I go scroll up slightly, there's this building form methodology as well. So other things that it's asking to optimize on. So you can do daylight modeling. You can try and make the floor more uniform by adjusting window positions and things like that.
Shade positions as well. Yeah.
Yeah, the position of shades, like overhangs, fins,
number
and
of
things.
fins. Yeah.
This building orientation, that would say that in the manual, that's an example in the manual where we rotate the building to try and minimize the demand, heating and cooling demand. So there's scope for doing these types of solving these types of problems as well. As I say, that example is just this.
The time's gone quite quickly today. We've got about 5-6 minutes left if you want to save some time for questions as well.
Okay.